Okay, good afternoon, Year 12. I'm afraid I'm on the key worker day today, so I can't be with you live in the lesson, but I should be available if you want to send me an email at red@theroyal.school during this lesson, so I should be able to get back to you, but you might just need to be patient, it might not be immediate. So we're having a look today at exponential functions and e to the power of x, which is something we'll cover in just a moment. So exponential functions are all to do with powers. So I've got 4 questions just to start us off. A past exam question about powers, and we want these written as exact fractions. So if you'd like to pause the presentation or the video, and then you can have a look at those questions, and when you unpause, I'll assume that you're ready to go through them. And so running through the answers to these then, if you've got 2/3 cubed for part A, we're going to need to cube the numerator and cube the denominator. So given us 2 cubed is 8 and 3 cubed is 27. For part B, we've got to remember that this negative power means a reciprocal. So we take our regular 4 squared, but then find the reciprocal of that. So 4 squared is 16, and taking the reciprocal for the negative power is 1/16. For part C, exactly the same idea. We're going to take our power of 2 first and then find the reciprocal of our answer. So take the power of 2 for both the numerator and the denominator. 1 squared is still 1, 5 squared is 25. So at the moment it's 1/25, but to deal with the negative power we need to find the reciprocal of that. So we'd get 25/1, or just 25. For part D, I'm going to do this in 2 steps. We've got 4/3 to the power of -3. So I'm going to do 4/3 cubed first, so cube the numerator, 64, cube the denominator, 27, and then we've got to deal with the negative part of it. Negative meaning reciprocal when we're dealing with powers. So 4/3 to the power of -3 will be the reciprocal of that fraction, so it'll be 27/64. That can't be simplified, so we're all good to move on. So where we're at with the course at the moment, you should have completed all the red parts between myself and Miss Ahmed's lessons. Pardon me. Miss Ahmed is at the moment covering differentiation and integration with you over here, and then I'm going to be covering this purple chapter that I've highlighted at the moment, which is going to be our exponentials and logarithms. So we're very close to moving on to the applied parts of the course, the statistics and the mechanics. So flip learning ready for next week, which will be the first week back after half term, is the exponential modelling and logarithms, which will be a little bit clearer once we've gone through today's lesson. So exponential functions that we're looking at today are all to do with raising numbers to certain powers. But that power is only in terms of x in this case. So we've looked at two different powers before, but 2 to the power of x here. So we'd start off by having a look in sort of GCSE fashion of a complicated graph. So we'd do it via a table of values. You may still be asked to do tables of values in the A-level exam, so do be aware of how to put these functions in on your calculator. So when you're dealing with powers, you will have the little raise function there to raise a number as a power. So we've got an x value of -3 for our first value here. So we'll be looking at 2 to the power of -3. Remember, that'd be the reciprocal of 2 cubed, and therefore it's 1/8. -2 and -1, same version of that. We've got the reciprocals of powers. Remember that anything to the power of 0 is 1. That's going to be quite key to these graphs and these functions that we're looking at. And also anything to the power of 1 is the number itself. So 2 to the power of 1 is 2. Obviously 2 squared is 4 and 2 cubed is 8. We can plot those on a graph. Now the graph has a couple of key features that are well worth mentioning. We've got a key point here, 0, 1. Anything to the power of 0 is 1, therefore a lot of the graphs, barring transformations, are going to be crossing at 0, 1 for exponential functions. We then rise rapidly as we're going up in increasing powers to the right, and then our numbers actually start to descend as we go to the left, but they just become smaller and smaller fractions. We never actually hit 0, and we never go into negatives in our y values with a regular power function. That means, of course, that we then have an asymptote, a bit like you've seen on the tan graph before, an asymptote on the x-axis at y = 0. Now, if your asymptote is on the axes, then you don't really need to draw it in as a dotted line, but you might see transformations of these, and it's very likely that you will. And therefore, if the asymptote isn't at one of the axes, then you're just going to need to label that in, and you usually might have to write it as a graph function as well. So like we said, y = 0 for the x-axis. So make sure asymptotes go on these graphs. So another thing you might need to see is graph transformations. Now we'll look at those in a little bit more depth in the future, but for the moment I just want to draw your attention to the fact that these might not be written exactly as you might expect. So here I've got y equals 2 to the power of x, which I'm going to call the function of x. So we've then got a graph transformation over on the left hand side of it, which is then listed as y equals 0.5 to the power of x. Now you can see here that it's actually a reflection of it in the y-axis, but a reflection in the y-axis is usually the function of negative x. So how do these two match up? Well, if our original function is 2 to the power of x, then if we want the function of negative x, which would give us this y-axis reflection, it would now be 2 to the power of negative x. Well, we've just seen that negative powers mean reciprocals, so we can actually find the reciprocal first and then leave the power as it is. So that would mean that this function is equal to 1/2 to the power of x. And of course 1/2 is the same as 0.5, so we could have it rewritten there. So you need to be a little bit careful with some of your graph transformations that are listed for exponential graphs, where they might have then used the power knowledge and indices knowledge to simplify some of the expressions, so it might not look immediately as you would expect for functions. A key thing you'll need to be able to do with these then is to plot yourself a graph of a more complicated function. Now, because you've got access to graphical calculators and you can just put this into your graphical calculator and copy the graph, so I'll put a couple more steps in there just to make sure that's not exactly what you're doing, although it'll be really, really helpful for you. And that's to fill in a table of values. Here it says give each answer as an exact fraction. Now, your calculators are a really good one, so they should actually be able to handle this as well, of just putting the values in and giving you an exact fraction. But we should be able to do it non-calculator as well. So we've got 2/3 to the power of x. So in the first case over here, we've got a power of -3. So I'm going to cube both of the numbers. So that's going to give me 8/27, and then find that reciprocal because we've got a negative power. So it'll be 27/8. When we've got a power of -2, I'll square my numbers, then find the reciprocal. So it'll give me 4/9 initially, and then 9/4 to find the reciprocal. Power of -1, we'll just find the reciprocal of that fraction, 3/2. Anything to the power of 0 is 1. Anything to the power of 1 is going to be the number itself, so that's 2/3. Squaring this fraction is going to give me 4/9. And then cubing the fraction is going to give me the cube of both the numerator and denominator, so it's going to be 8/27. So you should then be able to plot that graph, and this one you should be able to see actually, if we have a look, is going to cross at 0, 1, like a lot of these graphs will. But actually we get into our fractions on the right hand side, and our fractions are getting smaller here. You can see here we've gone from 1.5, 9/4, obviously we're at 2.25, and 27/8, we're over 3 there, so it's actually increasing when we go to the right in this case. So all we'd need to do is just show the rough shape of that graph there, and it's going to have this asymptote on the x-axis as well. And that's it, that's drawing the graph. So they're quite straightforward to draw. It says use your graph to solve 2/3 to the power of x equals 2. So you just draw a horizontal line. Now you'll have graph paper in the exam for this if they want you to do this problem. So draw a line at y equals 2 and just take your reading for the x value where that's the case. Obviously mine isn't an accurate version, so I wouldn't be able to take that reading. And later on in the course we'll actually show how you can calculate what that x value would be in a mathematical algebraic way called logarithms, but that's not in today's work. So here we might have some graph sketches. So here I've got the function of x equals 2 to the power of x, and we've got that drawn for us. It says use the graph to draw a sketch of the following, labelling the new coordinates of point A and any points of intersection with the coordinate axes. So these should be quite straightforward graph transformations. They're just applied to this new function. In the case of Miss Ahmed's chapter that you did before, you might have even been able to see these types of graph transformations occur, and you might have seen this function before but just not known what it was. So function of x plus 2 for part A, you should know that a plus 2 in the brackets is going to move our graph translation horizontally -2 units to the left. So that counterintuitive, -2 units to the right, i.e. 2 units to the left. So this is that counterintuitive movement when things are in brackets. So this means our graph, this 0, 1, is going to have moved from here, and it's going to move 2 squares over here. So we're going to have a point here. If it's moved 2 squares to the left, it's at -2, 1. But that's not what the point we're after. We're actually after a point where we intersect the axes. So we're going to need to try and find a point where it crosses here. Now, of course, at this point, our x value equals 0. So instead of 2 to the power of x, we've now moved our graph to 2 to the power of x plus 2. But we can still plug in that x equals 0 at this point, and then it would give us x to the power of 2 to the power of 0 plus 2, so 2 to the power of 2, i.e. 4, because this is a point 0, 4. And that's actually all we need for our graph axes and a graph sketch for this. We've got our axis intercepts, we've got our point that we did have moved over just for our purposes, and that's it. So in part B, we've got y equals a function of x minus 2. So in this case, the graph's going to move down 2. So it's going to cross the axes here at, instead of 0, 1, if it's moved down 2 squares, it's going to be 0, minus 1. So the graph's going to still look pretty much the same and go up like this. Now we are going to have a couple of different intercepts though. We've also got an intercept now on the y-axis, x-axis, where y equals 0. So what we'd have here is we'd have to rewrite our function in terms of this. So the normal function is 2 to the power of x, but we've got 2 to the power of x minus 2. At this point our y value is 0, and therefore solve this equation. 2 to the power of x equals 2 by adding 2 to both sides. And what power of 2 gives us 2? Well, it's 1. So x equals 1. And again, we might see some more complicated versions of finding these powers later on in the course, but not quite today. So this is 1 at 0, where it crosses the axis here. Now, another thing to remember here is that we'd originally have the asymptote on the x-axis. Now, because we've moved our graph downwards 2, we'd also need to put in here the asymptote, and that's going to be y equals negative 2. Instead of being the line y equals 0 here, we've moved it down 2 squares and get y equals negative 2 for our intercept, our asymptote there. And that's really graph sketching. A couple that might get a little bit more complicated, I'll just flick to a clean slide. So part C looks like it might be really complicated in order to get it accurate. When you've got two lots of the function of x, then the whole graph gets raised along the every y value gets doubled, and you don't really need to show it in any really posh way. You could actually draw the same graph. This is a little bit of a cheeky way of doing things. We could actually draw the same graph, but just change our axis intercepts. Instead of crossing at 0, 1, it's now going to cross at 0 and double our y value there. So we'll cross at 0, 2. And in fact, we're done on that. Then we've got y equals negative function of x. The negative's at the start of the function there, so that's going to be a reflection in the x-axis. So if our original graph goes up like this, our new graph is going to go like that, reflection in the x-axis. So if it originally crossed at 0, 1, then this is now going to cross at 0, minus 1. We've got our graph transformations done. And again, you might see combinations of those as things get more complicated. The other part of the function that you need to know is a specific function, which is e. Now, we've said, you might have seen on the video before, that when you look at these exponential values and exponential functions, the gradient functions of them are actually quite similar to the graph itself. So if you draw a graph of the derivative of those functions, it looks very, very similar to the graph itself, but there'll be ever such a slight difference whether it's to the left or to the right. But as soon as you get to one specific value, which is e, then you get the gradient function being exactly the same as the function itself, which sounds a bit complicated, but doesn't really need to be. So e, or e to the power of 1, I should say, is 2.71828 and carries on. And the key feature about this graph is that any given point, the function, i.e. the y value on the graph, is equal to the gradient. So if I have a look here, at 0, 1, you can see that the height of the graph here is 1, and what that means is our gradient at this point is 1. At this point here, you can see that the height of the graph is 4, and what that means is if you take a tangent to the graph there, then the gradient is 4. If we went backwards here, where you can see that the height of the graph here is about a half, then if you took a tangent to the line and and worked out the gradient there, you'd find out that the gradient was a half. So this is why this function is very special. It's used quite a lot in powers. You'll see it loads and loads throughout the course from now on. But this key feature that the function itself equals the gradient lends itself to actually differentiating this new function very, very easily. And we'll come to that in just a second. So you might need to be able to look at sketching some graphs of this function. So e to the power of x, exactly the same as our other functions, looks like this curve, doesn't hit the x-axis and crosses at 0, 1, because remember anything to the power of 0 is 1. So it's used as a big starting point. So we could use our graph transformations in exactly the same. Now I'm just going to do the three that are here, but you might want to have a look at the others yourself and check. So e to the power of negative x, well, if our original graph is e to the power of x, then if that x has turned negative, we're now doing the function of negative x. So a function where we're taking negative x in the brackets, remember, is going to be a reflection in the y-axis for this graph. So if our original graph goes upwards like this and crosses at 0, 1, if I change colour, then reflection of it is going to be here in the green line. So it's quite straightforward graph transformations. It's going to cross at the same point 0, 1 as well. So we've seen all of these things before, we just haven't applied it to this new function. So part C here, I'm going to look at now. Y equals negative 3 e to the power of x minus 5. So here we've got a combination of graph transformations going on. We've got a negative 5, which means the original graph's going to drop by 5 squares. We've also got a negative 3 part, which we could take in 2 stages, the negative part and then the 3 part. So let's have a look. We're really doing y equals, or sorry, I should put that as function of x. The function of x equals minus 3 f of x minus 5. So I would take this in stages and I'd show the examiner what to do. Again, you can plug this function in your calculator and it should plot it exactly, and you should be able to copy that out, but show those stages. So I'm going to show e to the power of x, then I could show 3e to the power of x. We're just going to times everything by 3, so it's going to cross at 0, 3 instead. I could then do the negative part of it. So this graph's going to then reflect in the x-axis for the negative part. So this is minus 3 e to the x. And remember that's going to cross at 0, minus 3 now. And finally, I could do the last part of the graph transformation, which is drop it by 5. So minus 3 e to the power of x minus 5. And if it originally crossed, or the one before crossed at 0, minus 3, if you drop it by 5 spaces, then it's going to cross here at 0, minus 8. So there's quite a lot going on with these, and it might be the case that you have a look at doing these first on your graphical calculator, then seeing if you can piece those together afterwards. But this should be the process that you need to have a look at in order to get through those. Now, of course, if our original graph had an asymptote at y equals 0 on the x-axis, this also has an asymptote along here at y equals minus 5, because remember we've dropped our graph by 5 spaces. So if you want to have a look through the other parts of those questions, you can, and get back to me on those. I'm going to move on to differentiating now. Now, differentiating e to the power of x is really easy, because we were saying that the function itself is the gradient function. So e to the power of x, so if the function of x is e to the power of x, then f dash x, or dy by dx, equals e to the power of x. But we might have some more complicated powers, and then it might have, for example, the function of x equals e to the power of ax, in which case it's quite a simple process still. The differential of it, dy by dx, if you've got it written in a slightly different format, is going to be a e to the ax. So we just find out what's happened to our x power, what's the coefficient of it, and we just bring that down to the front is our new power, so new coefficient. So if I've got e to the power of a half x, I just think that I've got a half x here, a half in front of the x. So all I need to do is to bring that half to the front and get a half e to the power of a half x. In part B here, it's as simple as, again, I've got a minus 5 in front of my x here, so bring a minus 5 to the front, and the power actually remains the same. So in a lot of differentiation, you're going to be reducing those powers. In this case, our power stays identical to what it was. So it's a little quirk of this exponential function. So if I've got minus 4e to the power of 6x for part C, the 6 comes to the front. So it's going to give, so if I times that by 6 at the front, the coefficient is already minus 4. So it's going to give me minus 24. And then the power remains the same, e to the power of 6x. And here I've got 7e to the power of a third x, so the third gets brought to the front. 7 times a third will be 7 over 3 e, and the power stays the same. So it isn't so much a difficult proposition as it is just a new proposition to learn here. Now these can be mixed up into some more complicated formats, so I just want to run through a few of these. So here, the part A, we've got 3e to the power of 2x plus e to the power of 4x. So we've got these separated out. There's two separate e functions here, so this is nice and easy to go forward with it. Bring the power to the front, or the coefficient of x to the front, so I'd have 6e to the 2x to differentiate the first term, and the same idea with the second term. Bring the coefficient of x to the front, so that's a 4e, and then the power remains the same, 4e to the power of 4x. But part B, we might just need to be a little bit careful with. 6e to the minus 2x, it should be straightforward to differentiate. But 5 over e to the power of x, it's sometimes nice to write these as single powers of x rather than fractions. So I'm going to write that as 5 times e to the power of negative x. Remember, negative would mean the reciprocal, so that would explain the bottom part of our fraction. You could then differentiate, bring the negative 2 to the front, gives us a negative 12e to the minus 2x. And over here then, I'll write the plus in here, but we're going to bring the negative part to the front. So it's a negative 5e to the minus x. So I'd get rid of the plus when I simplify my final answer. If you've got something like part C, that's actually something we'll learn to differentiate a little bit later on in the course straight away. But for the moment, all we need to do is actually just expand the brackets. Remember, when you multiply powers, you add the powers together. So if I've got e to the power of 2x times e to the power of negative x, it becomes e to the power of 2x add a negative x, which of course would simplify down to just e to the power of a single x. Then I've got a minus 4 times e to the power of 2x, so that's going to stay the same, minus 4e to the power of 2x. And then I could differentiate by bringing the powers to the front. Well, this one's going to stay the same. And this one I bring a 2 to the front, so minus 8e to the 2x. And same idea with part D here. I could rephrase my first term as e to the power of negative 3x. That equates for our 1 over e to the 3x. Leave my powers in there. Then I need to just expand the brackets here. So I'd have 2e to the minus 3x, and then minus e. And then we're going to add those powers together, so negative 3x plus 5x is going to give us a positive 2x when you add your powers, just as you would in a normal indices function. Bring our coefficient of x to the front, minus 3 brought to the front gives us a minus 6e, and leave the power the same to the power of minus 3x. And in the second part then bring the coefficient of x to the front, so that's a minus 2e, and leave the power the same, the power of 2x when it's differentiated. And that's just pretty much done with exponential functions. One of the others to watch out for, I've mentioned index laws before in this. So if we had something like e to the power of 2x plus 4, well, what we might want to do is, there's obviously not just a single coefficient of x there to bring out to the front. So what we'd actually do is actually think about our indices laws and actually separate this out. If I've got a 2x and a 4, well, if they're added together, that means they might have existed initially as two terms that were multiplied. So I could actually rewrite this as e to the power of 2x times e to the power of 4. Now, e to the power of 4 is just going to be a constant term. Remember, e is just a number, despite us using the letter for it. So if it's e to the power of 4, that is just a number. So actually, I can differentiate this by bringing our coefficient here now to the front. So I'm going to do 2e to the power of 4. Remember, that is a constant term. Then e to the power of x. Now, in this case, 2x, I need to leave the power the same. Now, if you wanted then to wrap things back up into a simplified form, we can do our multiplication now using our index laws. E to the power of 4 times e to the power of 2x is going to become e to the power of 4 plus 2x, or 2x plus 4 for our final part of the answer. So you can separate terms out there. You might learn a quicker way of doing that, but that's going to show us how and why it's done. So there's quite a few things I've gone through here. I will move us on to our independent work now, because you are losing period 6 for your well-being, and this should be enough time for you to have a look at your independent work. Now, you should have a chance then to have a look through exercise 14a and 14b. And because we're at an early point in the chapter, there aren't too many exam and problem solving questions coming in just yet, but it's essential we lock down these questions. So I'm setting you questions 4 to 7 from exercise 14a and all of question 14b. There's 7 questions, but they're not particularly long ones to get done. So if you can get that done now, again, I will not be looking for this until kind of a week's time for my lessons. It's a bit harsh asking for this in by the end of Friday when we have a lesson on a Thursday. So I'll be looking for this in a week's academic calendar. So we'll be looking for this on the at the end of the end of the first week back after half term. So I should be available, as I said, on red@theroyal.school if you do need any assistance. So please send me an email if you need any assistance. So good luck with your work, and I hope to hear from you if you've got any problems, and so I can give you any help with that. Thank you very much. I'll speak to you soon.